So here we're given our voltage as a function of time, as shown in the image in the top left below, and a capacitance of 5 millifarad. We want to determine the current, power, and energy as a function of time. To begin, we first have to have a functional description of our voltage as a function of time. We see from 0 to 2 seconds, our voltage is linearly increasing from 0 volts to 100 volts. At 2 seconds, our voltage then begins to decrease linearly up till 3 seconds, where it reaches a value of 50. After 3 seconds, our voltage remains constant. Thus, for us to begin, we need to determine our time rate of change of voltage to determine our current running through our system. That is, our current is equal to our capacitance times our time rate of change of voltage. Our capacitance is 5 millifarads, and our time rate of change of voltage is 50 volts per second. Therefore, we have a constant current of 0.25 amps entering our capacitor. Our power is equal to our voltage times our current. Our voltage is equal to 50 volts per second times T, and our current is equal to 0.25 amps. Thus, our power is equal to 12.5 T. This has units of watts. We see our power is linearly increasing as a function of time. This expression is valid only in the range between 0 and 2 seconds. Lastly, to determine our work, we have to take 1/2 of our capacitance times our voltage squared. We have 0.5 times 5 millifarads times our voltage, which is 50 volts per second squared. This gives us a value of 6.25 T squared. And we see parabolic increase of our energy stored within our capacitor. At 1 second, we have 6.25 joules stored within our system, and at 2 seconds, we have 25 joules of energy stored within our capacitor. Now we have to move to our next time interval, between 2 and 3 seconds. Our voltage is decreasing from 100 volts to 50 volts. That is, our current is equal to our capacitance times our time rate of change of voltage, and we have minus 0.25 amps. That is, a quarter of an amp is leaving our capacitor. We are supplying energy to our system. We are no longer accumulating energy within our capacitor. Our power, which is equal to our current times our voltage, is equal to minus 0.25 amps times our voltage. Our voltage is described as minus 50T plus 200. Recall an equation for a line. Y is equal to mx plus b. M is our slope, i.e. minus 50. B is our y-intercept, i.e. 200. So our power is 12.5T minus 50 watts. And this is valid within the range of 2 to 3 seconds. At 2 seconds, we have minus 25 watts within our system. And at 3 seconds, we have minus 12.5 watts. Lastly, our energy, which is equal to 1/2 of our capacitance times our voltage squared, is equal to 0.5 times 5 millifarads times the quantity minus 50T plus 200 volts squared. Or we'd have 0.0025 farads times minus 50T plus 200 volts squared. We see that our energy starts at 25 joules at 2 seconds, then decreases to 6.25 joules at 3 seconds. Lastly, in the remaining time interval from 3 seconds to infinity, our time rate of change of voltage is equal to 0. Thus, our current is equal to 0 within our system. Our power is equal to 0 within our system. And our energy is staying constant, where we have 1/2 of our capacitance times our voltage squared. Our voltage is a constant 50 volts. Thus, our energy is 6.25 joules.